Okay, here we go. Solids number 2. What are solids? In this case, prisms and 3D. I guess that's a topic more than a theme. 3D is a topic of solids. All right, so go through our chart here. What shape is this right here?
Line.
Line? How many dimensions? Right? One dimension, just whatever that line is. Doesn't matter what angle or whatever it is. Along that line is one dimension. Fair enough? Okay. Shape?
Rectangle.
Rectangle, I tried to draw. And number of dimensions?
2D.
2D. What are they? Generally speaking, you know, in math at least, we've got the X and the Y, but you're talking about horizontal and vertical. Fair enough? Horizontal this way, like looking out the horizon. Vertical, up and down. So 2D. Okay. Shape?
Cube.
Cube. How many dimensions?
3D.
So X, Y, and in math, what do we call the dimension that goes between us? What's that dimension
Depth.
called? Depth is true. In math, I'm thinking of the Cartesian coordinate plane, so X, Y, and Z. But depth is another way of saying that. You can call these dimensions any number of names, as long as you've got those 3. Okay, what is the 4th dimension?
Time.
According to physicists, how many dimensions could there be?
1.
I think they speculate infinite, right? But imagine you're a creature that can only see in one dimension. You see this. That's all you see. Imagine jumping to a human being who can see in these dimensions, and you see what we see. What if you could see in 20D? How much more could you see that this creature can't see, or whatever we are, right? Does this make sense how the idea of dimension, like when you watch a sci-fi movie and they talk about going to another dimension, maybe that's what it relates to, right? The fact that if you could see in 20 dimensions, you could see things that a person in 3D can. Okay, or a person who sees in 3D can. All right, let's start to do some shapes. Let's start with a cube again. So here's our cube. There you go. No shading on this one. When there's no shading, which do you see? Do you see this face closer to you, or do you see this face back here closer to you? Which one is closer to you? This one or this one?
Switches.
The one in the back? Is that what you said? But interestingly, you said the one in the back was closest to you. Do you see the irony of that? But I know what you're saying. Your eye is seeing it closer to you, right? How did you know that's the one in the back? Well, we could do some things to... First of all, it's a trick on your eye, right? Because how many dimensions is the board?
1. 2.
2. Why is it 2? Because it's not just this. Literally one dimension would be just like a string pulled tight, right? That's one dimension. That's how thin it is and nothing it is, right? Once you go to a flat surface like this, you've got the X here and the Y there. So this is 2. The board's 2. But your eye is seeing how many here? Your eye is seeing the 3rd dimension. So is there 3 dimensions on the board? It's a trick. This image is tricking your eye. How can you help your eye see which face is up front? If we make these into here we go. Let me get it right. There. Now which face is closest to you? This one over here, maybe? I guess I could have drawn this a little bit differently. But the dashed lines represent what to your eye?
That's like in the back.
The back, the back, and the back lines are hence or therefore hidden, all right? So when you take architecture drawing or drafting or CAD drawing, anytime you have a hidden line and you want to show it back in there, you do it with dashed line. Okay, let's talk about volume. This dimension here, from here to here, what can you call this? What are some names of the dimension? This way? From here to here. What would you call it?
Length.
What would you call that dimension?
Oh. Line.
It is a line? This
Is
one
it
here?
Length.
Length?
Length.
How many would say length? Does that sound familiar? So length Okay, and along those, now that you kind of know where I'm headed, I kind of didn't give you any hint there at all right? What's this dimension called here as you go toward the back? Width. Any other names come to mind? What'd you say? Depth. Good. Does that make sense? We can use different names. It doesn't matter. There's only those dimensions going on. This one, this one. How about this one? How about this dimension this way? What?
Height.
Yes, height. Yep, and you might generically call it horizontal, vertical, and depth would be between us. Okay, so how do you calculate volume? Think of, how many of you use like milk at home? Like you have a jug of milk, a gallon of milk maybe, or maybe a half gallon is the smaller carton. When you pour that from the jug or the container into a glass, that milk is taking up a volume. It's got 3 dimensions to it, right? So imagine pouring milk into this cube and the milk filled up to here. That would be the total volume of this. How do we make a calculation? We literally multiply length times width times height. We multiply the 3 dimensions to find out a number that we assign to what volume is for that shape. The milk might help your brain better though, by filling this up with milk. That's how much it can hold, that's its volume capacity. All right, let's take the cube and stretch it and go like this. All right, not too good, but it's okay, I guess. I'll make through. Same thing, you've got a length down here, length, a width here, and a height here, H-E-I-G-H-T for height. How do you calculate volume of this? Same thing, length times width times height. By the time you calculate the 3 dimensions, that's how you get a 3-dimensional number. You literally multiply 3 by each other. What if you took the milk in this cube and you poured that milk into this shape here? Would it fill it all the way up? So I got milk in this cube, and I pour it into this shape. Would it fill it up? I don't think so. I mean, just physically look at dimensions. Let's assume I'm trying to draw to scale, right? And you took this milk, filled it up, might fill it up to about there, right? So is the volume of this shape smaller or?
Bigger.
It's bigger. It has a larger capacity of volume. Does this make sense? And the number assigned to that by multiplying length times width times height would give you a comparison. You could say the volume of this one is so many cubic units. Why is it cubic? Because it's units times units times units. And this one's going to fill up, be so many. And so we could say, hey, this was such a percent of that one, right? All right. Let's take this prism, because this is called a rectangular prism, and let's push it over. We're going to make it this word here. Okay, this word is oblique. Everybody say oblique.
Oblique.
Now my brain wants to read it differently. What does my brain want to read? Oh, I want to read oblique.
Oh.
Right? So, I don't know, French word or something? Oblique is the way it is, all right? So oblique, oblique. What does it mean? It means slanted with some details included. So let's take this rectangular prism and draw it like this. I have to concentrate with all my energy to do that. Can you tell it's pushed over?
Mm-hmm.
Like almost somebody took and pushed this way, right? But notice the top is flat and the bottom's flat. So it started like this and somebody pushed it. And imagine the shape stretching. It would have to get longer to go that different distance. Okay, so here's my sort of question for you. And I should have drawn it right next door. Let's say this slanted one is the same perpendicular height as this one. So you started here and you pulled one over. This one's pulled over, the oblique shape. Which one has more volume capacity? Does this one have more volume? Does this one have more volume? Yeah. Your eyes kind of went like, yeah. Like, that was like a maybe, yeah. And it looked like maybe. Why would you think maybe? Because as you stretch it out, maybe it's longer.
Mm-hmm.
So my brain is with you on this. My brain wants to think this has a larger capacity of volume. The truth is, it doesn't. It has the same capacity of volume as long as this height, which is perpendicular to the base, is the same as this height, which is perpendicular to the base. Why? Because the volume of this one too is length times width times perpendicular height. And so if this perpendicular height is the same as this one, and the length and the width are the same, then it's going to be the exact same calculation, length times width times height. This one's going to be exactly the same as this. So the conclusion you have to draw at the moment is, even though it's oblique and slanted, it has the same volume capacity as the non-oblique or non-slanted. All right, let's look at this. What shape is this? Man. Shape?
Triangle.
It looks like a Dorito, right? It's about the size of a Dorito?
Mm-hmm.
Okay. That's a triangle. How do you calculate? Oh, let's do this. Watch what I do to it. Okay, what did I make it into?
Triangular prism.
It's a triangle, now stretched out into a height. So how many dimensions was the triangle?
2.
2. And by stretching it out, I added what to the shape?
3D dimension.
The third dimension. So now this is a 3D triangular prism because it's a triangle that's been elongated or stretched out. Make sense? Okay. How do you calculate the volume of this? First, we want the area of the Dorito or triangle at the end. What's the area of a triangle? It is 1/2 base times height, b times h. What's the base of the triangle? The base is this here. What's the height of the triangle? It's the perpendicular distance from here to here. That's its height. So if you took this triangle out and drew it sideways like this, you'd have a base along the bottom here and a height here. And notice it's the perpendicular height here, the h. So that'll give us the area. Then we multiply this by the height of the whole shape, H-E-I-G-H-T. And this would be times height of shape. Right? I don't know why my handwriting is getting really bad, worse than even normal. And now the same thing applies. If you were to take this Dorito and stretch it over like this, there, did I almost get it? What have we made the triangular prism into? Or no, what word do you use to describe now the triangular prism?
Oblique.
Oblique. Everybody say oblique? Because it's now slanted over. And if I drew it right, I tried to keep the top here and I tried to stretch the top over. It looks like I made it a little bit longer, but as long as this height all the way across, yeah, I kind of did. I kind of made it way too high here, I feel like. So I'm gonna ruin my own idea. If this comes straight across here, it'd be like this, and this would be like this. There. And so the perpendicular height of this, from here to here, this height, perpendicular because what's the angle right there?
Right.
Right. What's another name for right? How many degrees?
90.
That's your 90 right there. As long as that height is the same as this height, and the triangle has the same dimensions here and here, it will generate the same formula. 1/2 base times height, that's of the triangle, times the perpendicular height of the shape. Okay? This is the volume formula, V equals this. And if you were to pour out milk into that shape and it filled it up, that's the idea of what volume is. Volume is that. Because milk fills in all the corners, right? There's no voids or holes left in there. Everything's filled in a volume. It's covering all that space in there. Okay. Let's see what else we got. Let's do one other. Let's do a trapezoidal prism. So here's a trapezoid. A trapezoid has a base, two sides, and another base. That's a trapezoid. Normally we draw it the other way when we draw it, but you can draw it this way also, right? Now let's go down and connect this to this. There you go. And there would be a hidden line back through there. There's a trapezoidal prism, 3 dimensions. How do we calculate? Oh, let's draw the oblique shape would look like. I'm going to challenge myself here. Man.
Oh wow.
Right? That's awesome. Yes, that's exactly my thoughts. Okay, as long as the height of this coming here and here, as long as this height is the same, then and all the other dimensions are the same. For example, this is base 1, this is base 2, and this goes back to the area, by the way, when we were doing area of shapes way back when last semester, we were doing area of trapezoids, right? So the area was base 1 plus base 2, base 1 plus base 2, divided by 2, so we'd get an average. Whoops, I'd like my parentheses to be here. So we'd get an average of the 2 bases times the height of the trapezoid, so times an h here, times the perpendicular height of the whole shape. So times perpendicular H-E-I-G-H-T, height. Wow, it's getting, this is, the handwriting and everything's getting really bad. This would be the volume if you were to pour milk into this shape and it filled up, and it was those same dimensions, including the perpendicular height. You would be able to take the milk from this one, pour it into this one, and it would exactly fill this one also. Okay, trapezoidal prism. So let's go through some of these. Vocabulary. Oblique is slanted or skewed with the top and bottom parallel. So I didn't say that yet, but I need to. Notice that the Dorito on top and on bottom, as this thing gets stretched out, those two are parallel to each other. So you're using 2 concepts, right? One is, okay, if these 2 are lines, are these lines perpendicular? What do you say about these 2 lines?
Parallel.
These are parallel. If it makes a plus, these 2 lines are
Perpendicular.
perpendicular. Okay, so you're back to some concepts from way back when. We're just dragging in, and I probably should have reviewed them a little bit better up front. So we're talking about volume. We're talking about the prisms. We're talking about oblique versus regular prisms. Regular in terms of not oblique. And you're just talking about your concept of 3 dimensions or 3D. Okay, that's good for now.